Alright, how's it going everybody? I am here making this video on Thursday, April 22nd, and today we're going to be talking about forced harmonic oscillators. Remember, as we talked about in the last video, our wrap up to this semester, we looked at a little bit of a topic in Chapter 5 in the previous video. This week we're going to hit two sections of Chapter 4. Next week we're going to hit two sections of Chapter 6, and that will be our conclusion to the class here. So we're going to talk about including forcing terms in our second order differential equations this week. You'll see, again, if you're looking at the section titles above me, we're going to in general talk about forced harmonic oscillators today. In the next video, we're going to see that we need to do a little bit of special consideration when we have sinusoidal forcing terms, when we have trig functions being included in these second order differential equations. We need to just think a little bit more carefully, or I should say guess a little bit more carefully, as we'll see in this video. Next week in Chapter 6, we'll discuss Laplace transforms, and you will see that they are going to help us solve second order differential equations, but are quite different strategy-wise and execution-wise than everything else we've done this semester. So that's a really interesting calculus technique there for helping us solve some, really coming back to doing the calculus is what's going to happen next week here. So where are we at here? So far, all of the oscillators that we've discussed have been unforced, meaning we've talked about this mass on a spring. We've talked about like pulling the mass and releasing it and then just letting it go. Or maybe pulling it and releasing it even with some initial velocity, but still then just saying, now let's just watch the system over time. And we see that things like if there's a damping scenario, that it eventually calms down to just being at the origin right there, right? The point is, we haven't applied any force to these masses on the springs after the release. We've just let them go. Now what we want to ask is, what happens if there is some external force being applied to the mass that's on a spring throughout the process here? So you can imagine like a child being on a swing. In that case, you're constantly applying, or I shouldn't say constant, that's a bad math word right there. You are periodically, that's maybe our special words for section 4.2 right here, applying a force to that system over and over again. It is an oscillator because it's a child on a swing. You know, if a child's on a swing and you just give them one push, or even better, if you just pull them back to some initial position and let go, then they're going to swing back and forth. And because there is damping associated with some friction in the hinges up top, it's going to eventually settle down to the child just crying at the bottom of the swing right there. However, what we know is that if you are periodically applying a force, then that's not necessarily going to be the long-term behavior. It's not necessarily just going to be coming to rest at the bottom down there. So what we want to think about now is what happens if there's an additional force being applied to our system rather than just a setup and a release. So what we need to do is we need to include a new term in our second order differential equation for the harmonic oscillator so that we have a term that represents that force over a time. So let's rebuild our harmonic oscillator equation one more time. We've written this stuff out a whole bunch of times by now. I'm going to do it again. There's just going to be one extra term in there. So what we know that we've got here is that we've got a damping force. And we know that damping forces are going to be forces like friction. Friction opposes velocity, so that's why we call that term a negative bx prime, x prime being velocity, b is like the coefficient of friction right there. We also know that we have a spring force, and again, we keep on referencing the specific example of spring force, but there's lots of forces that are representative of this here. Spring forces oppose position rather than velocity, so that's why we get opposing is negative. K is the strength of the spring. X is representing our position because springs oppose position. And importantly, we now have a forcing function. The force that we apply might change over time, so we'll think of the forcing function as being a function of t here. And the point is, we aren't establishing specifically what this is yet. We just want to say it's some generic forcing function. Function does not have a G in it. Function. So we'll choose some specific forcing functions. Today we're going to look at a couple families of functions that we could have for f of t. Hopefully you're anticipating in section 4.2, this f of t function is going to be things like sines and cosines, or sinusoidal forcing functions there. So we put all these things together with Newton's second law of motion, force equals mass times acceleration. We know that mass times acceleration should be the same thing as mx double prime. Right? The second derivative of position is our acceleration. What are all the forces we're experiencing? Well, we've got our damping force, we got our spring force, and we've got our forcing function. That's the force that's being applied over time. So we rewrite this as mx double prime equals we've got a negative bx prime, we've got a minus kx, and we've got a plus f of t. And we're going to do the same thing we've done every time we've done this same exact process here, is just add these two terms to go hang out with the x double prime term over here. The one major difference being we're going to leave our f of t alone over here. So I'm seeing mx double prime plus bx prime plus kx equals f of t. And it is pretty typical, by the way, for us to just do a little bit of division here by m and to rewrite this guy as m, or just x double prime. It's pretty typical to make sure that you have just a coefficient of 1 on the x double prime, just for like the sort of standard form that these are written in, px prime plus qx equals f of t. Clearly, we just divided everything by a constant here, so our forcing function has certainly been divided by an m term that's right there. That's just a constant multiple right there. So by the way, I do want to kind of name this thing right here, just so that we can remember all the ridiculous naming schemes that we get here. This is a second order linear, because it can be rewritten into a system form, constant coefficient, non-homogeneous, because we don't have everything on one side, non-autonomous, because it now is going to have some terms that have a t in them, differential equation. Right, so our outrageous name for this thing right there, all those modifiers. Remember, non-homogeneous means it's not everything's not written on one side. We typically keep our x terms on one side and our t terms on the other. It's not autonomous because we have an f of t function right there. This is going to have some dependence on time, right? The force that we're applying might be, if we're thinking about the child on the swing, it's really like we're only actually applying a force every once in a while, right? So the force that we're applying is going to change over time, right? So what we'd like to do is we'd like to find solutions to equations of this form, but our previous eigen techniques are no longer going to work since we can't convert this to a linear system. By the way, I was just thinking that right there. This is not a linear system necessarily, because that f of t is not necessarily going to be some linear term in x or y right there. So the point is here, with that additional term, we can't any longer convert these into systems where our equations are of the form ax plus by and cx plus dy, because we're going to have that extra forcing function f of t being involved there. So that means that sort of breaks our previous eigenanalysis. However, it turns out there's still going to be a really close association between what we've done in the past and what we're going to do here today with that. So it's not like we're just discarding that. It's just no longer going to be like the whole thing here. So we need to come up with a technique for solving these differential equations. And I mean, what are we going to do? Well, what have we done all semester? And we want to come up with a technique for something new. We've basically followed the same trend the entire semester. The two things that we've done to come up with basically all of our solving techniques is we have guessed a solution and then verified that it works. And then in situations where it's hard for us to even make a guess, we've said, well, what did we do in the past? We imitated previous solution techniques, right? We're going to do both of those things pretty aggressively all day today and in the next video as well. We're going to make a whole bunch of guesses. We're going to do a whole bunch of imitation of previous techniques out there, and that's going to kind of get us all the way there. So as our first example here, let's go ahead and solve the forced harmonic oscillator. So this is how you know it's an oscillator, because we have a position function as well as velocity and acceleration being involved there. We can see that the forcing function associated with this forced harmonic oscillator is e to the negative t. So it looks like the force that's being applied to this system is going to exponentially decay over time. So it looks like in the long run, we're not really applying much force, but maybe early on in time, there's this additional force being included into the system right there. So this forcing function is a bit interesting in that it decays to 0. That's not necessarily going to be the case, right? Again, with the child on the swing, you should be thinking about being like a sine of t function right there. We're applying a lot of force sometimes and essentially no force other times, or actually no force other times if it's the child on the swing, right? So we want to solve this thing, but we don't know what we're doing, right? So what I like to first say to myself is like, this is hard. What would make this problem easier for us to do? If this problem were stated differently, how would you like it to be stated so that you would know what to do? We only know how to solve the related equation. of x double prime plus 5x prime plus 6x equals 0, right? This is what we know how to solve. We learned how to solve this back in chapter 3 in section 3.6. Pretty dang easy. In fact, I can do this like very quickly, right? We're going to get lambda squared plus 5 lambda plus 6 equals 0. I'm going to recognize that this factors down into lambda plus 2 and lambda plus 3. So I'm seeing that we're getting eigenvalues of -2 and -3. And that says to me I can just state my general solution as x of t being k1 e to the -2t plus k2 e to the -3t. All right, that's our solution to this nearby equation right there. Right, that's not what we're looking to solve, right? But here's the thing: if we used this x of t equation right here, if you plug this in into this equation or into this equation, what you know you're going to get out is just 0. This is the components of a solution that go to 0 when plugged into the differential equation on the left-hand side. So what this means to me is that this solution that's associated with the homogeneous equation, meaning the equation that's equal to 0, causes the entire, I remember that typo and not fixing it, causes the entire left side of the differential equation to be 0. What this means is that this can be included in what we're actually going to find for our solution. And by the way, I should call this x sub h of t because that is the homogeneous solution to x. It is the solution if the right-hand side were equal to 0. And so the point here is this could be included in our actual solution to the actual differential equation we want to solve because these are the components that would just go to 0 when you plug them in to the left-hand side. What we still want to include in our solution, though, is the components that are going to go to e to the -t when we plug them into the left-hand side so that we actually get the remaining component on the right-hand side over there. So the point is that even though this isn't the problem that we've been asked to solve, all the stuff that I just wrote right here, it seems like these components could be included in our solution to the actual differential equation we want to solve because these components will just go to 0 on the left-hand side. So we would just need an additional term or terms over here being tacked onto this. That would be the terms that go to e to the -t when they're plugged into the left-hand side. So the point here is, as part 1 to this problem, we complained that we didn't know what to do because of the e to the -t. We whinily said, well, I wish that was just a 0 over there, then I could solve it easily. And it turns out this is actually a practical contribution to our overall solution. It's just not the whole thing anymore. This is the parts that would go to 0 on the left-hand side. Now we just need to find the parts that would go to e to the -t on the left-hand side to match the right-hand side. So these can be, as I say in the paragraph, these can be included in our full solution without affecting our ability to also get the forcing function of e to the -t to pop out as well. So in general, what this says to me is that our solutions for our forced harmonic oscillators are always going to be of this form, where we have our homogeneous solution, the solution that we got out if things were equal to 0, added on to the particular solution, meaning the particular terms that we need to agree with the e to the -t right there. Above, we just found the harmonic we found the homogeneous component of the solution that causes the left side to be 0. Now we want to find the particular solution associated with finding that e to the -t to be cropping out on the right-hand side. To do this, let's just make a guess. So notice, let me scroll back up real quick here. We said that what we were going to do today was guess and imitate previous solutions. So far, we've realized that imitating our previous solution associated with the 0 being on the other side of the equal sign actually helped us get a component that can be included in our general solution. Now to get the remaining part, we're going to just guess what that remaining component is going to be. Our forcing function that we want to get out is e to the -t. And it needs to be composed of 0th first and second derivatives, right? 0th first and second derivatives of some function, right? Of the particular solution. So what seems like a reasonable guess for x in this case right here, remembering that we're looking at x double prime plus 5x prime plus 6x equals e to the -t. Sorry, I want to make sure that those are very clear right there, x double prime. So what I'm thinking that we should guess for x and our particular solution for x Well, it seems to me like e to the negative t is a reasonable guess right here because I'm thinking derivatives of e to the negative t just give you back more e to the negative t, right? So let's go ahead and just guess this for our particular component right here and see what we end up getting. If we do this, then we're saying that our derivative should be negative e to the negative t, and our second derivative is going to pop out another negative, so it's actually back to being e to the negative t. And we can go ahead and plug this stuff in now. And what are we going to get? Well, our second derivative is e to the negative t, plus 5 times our first derivative, which is negative e to the negative t, plus 6 times the guess, which is just e to the negative t. Put all my substitutions in parentheses there. And we're hoping that's just going to work out, right? I mean, that's what's on the right-hand side. I'm just wondering, like, is this legit right here? And so what I'm seeing is positive 1, negative 5, positive 6. It seems like this came out to be 2e to the negative t equals e to the negative t there, right? Not quite right. But it seems like it was really close, right? It seems like that was still not a terrible guess on our part right there. It just seems like it didn't quite work out to be exactly the guess that we were looking for here. So what we want to do is we want to just beef this up a little bit here. It wasn't quite right, but it was really close. So what we're going to do is we're going to use the method of undetermined coefficients. This is kind of like something you guys have already seen before. We're just sort of formalizing the name here. The method of undetermined coefficients just says make your guess, but only guess up to a constant multiple of the structure of your guess, and then go back and figure out what the constant multiple needs to be. So instead, let's guess a more generic version of k equals e to the negative t, and now we can see that our x prime of t should be negative k e to the negative t. X double prime of t should be positive k e to the negative t. And now we can go ahead and plug this into our differential equation and see if we can find a value of k that's going to make this work out. So I'm getting k e to the negative t plus 5 negative k e to the negative t plus 6 k e to the negative t. Equals e to the negative t. Now in this case, I'm getting the same thing as above, just with the factor of k over here. So it seems like I'm getting, for the positives, I've got a total of 7k e to the negative t. And here I've got negative 5 of them. So it looks like I'm getting 2k e to the negative t equals e to the negative t. And it looks like k equals 1/2 will make this work here, right? So it seems like we're going to find a particular solution to be 1/2 e to the negative t. It looks like that's the component that needs to get included so that we actually arrive at our forcing term on the right-hand side. So basically what it seems like has happened now is that we have found a general solution So our general solution is going to be, remember, it's always going to be, for all these forcing second order differential equations here, the homogeneous solution is all the components that would go to 0 when plugged into the differential equation. The particular components are the components that turn into the forcing term when plugged into the differential equation. So we are claiming that our general solution to this is going to be the k1 e to the negative 2t plus k2 e to the negative 3t that we found above, plus 1/2 e to the negative t. So this should be our general solution to this second order forced harmonic oscillator right here. So let's go ahead and verify this, and in doing so, we'll kind of see why this actually works out. So what I know I'm going to need to do right here is I want to be plugging in my appropriate 0th, first, and second derivatives into this equation. So let's go ahead and compute those right here. And man, if you can't stop highlighting this Microsoft Word, I'm going to freak out. Okay, there we go. So I want to be taking a derivative here. So x prime of t is going to be negative 2 k1 e to the negative 2t minus 3 k2 e to the negative 3t, and then minus 1/2 e to the negative t. And my second derivative here, I'm just popping up more constants. So I'm going to get a 4 k1 e to the negative 2t plus 9 k2 e to the negative 3t plus 1/2 e to the negative t. And so, what are we going to get here? Obviously, there's going to be a large grouping of terms, but what we know to expect is that almost all, I mean, literally, we're expecting that when we group up all these and take some constant multiples like times 5 and times 6, that out of all 9 of these terms, everything's going to wash away, and we're expecting to literally just be left with an e to the negative t right here. So let's go ahead and see if that does, in fact, happen. So, x double prime. X double prime is 4k1 e to the negative 2t plus 9k2 e to the negative 3t plus 1 half e to the negative t plus 5 times negative 2k1 e to the negative 2t minus 3k2 e to the negative 3t minus 1 half e to the negative t plus 6 times k1 e to the negative 2t plus k2 e to the negative 3t plus 1 half e to the negative t should be equal to e to the negative t. That's what we're trying to verify is happening right here. All right. So what we want to end up seeing now is this. What I kind of want to identify in this case right here is you should notice that these terms are all of the terms that are associated with our homogeneous stuff, whereas these terms are all the terms that are associated with our particular solution. So what I'm going to do is I'm going to group all of them up to hang out with each other here. I'm going to say this is our x sub p, and this is our x sub h, right? So for kind of some color organization right there. So what I'm going to do is I'm going to group up all the terms with the blue bars that are associated with our harmonic or our homogeneous solution, and with the purple, all the ones associated with our particular solution here. So what I'm seeing I'm going to get is 4k1 e to the negative 2t plus 9k2 e to the negative 3t. Over here, my next grouping is, it looks like that's a minus 10 right there. Minus 10k1 e to the negative 2t minus 15k2 e to the negative 3t. And over here, I'm going to get plus 6k1 e to the negative 2t plus 6k2 e to the negative 3t. And that's my first grouping. That's all my blue terms here. Then for my pink terms here, I'm going to get a 1 half e to the negative t. I'm going to get a minus 5 halves e to the negative t. And I'm going to get a plus, and it looks like this is a 6 halves right here. And so what we can see here, again, I want to make sure I'm marking this off appropriately here. These are all the terms that are associated with our homogeneous solution, and our claim is that these are all the things that we should be able to plug in to the differential equation, and we should just get out 0 on the other side. I mean, that's literally the math that we did right here, right? When we did this math right here, we said, well, listen, if all we wanted to get out from all these x terms on the left-hand side was 0, then we could give this as our solution. So I'm expecting that that whole blue chunk down here is going to literally just give us 0, right? So here's what I'm seeing here. It seems like and I guess I should get some more colors here to group these guys up. Let's see the K1s here. The K1, K1, and K1. Do those all cancel? It looks like they do. It looks like I'm getting the 4, the negative 10, and the positive 6. What else do we see out here? I see that I've got my K2 terms, and there's my K2, my K2, and my K2. And I see 9 and 6 makes 15. And a negative 15 makes 0. Over here, I'm expecting these terms to be the terms that associated with my particular solution. Those should just be giving us our forcing term on the right-hand side. And I do see 1 plus 6 is 7, minus 5 is 2, 2 halves is e to the negative t. So this says components associated with homogeneous solution go to 0. Components associated with particular solution go to to the forcing function. All right. So pretty cool. So again, it looks like what we want to include in our general solutions then is we want the pieces of x, these first two terms, that are the terms that are eventually going to zero out when we plug them back into the differential equation. The remaining term, the particular solution, is the term that is going to contribute to eventually being the forcing function on the right-hand side. So that's mathematically how this is always going to work out, is that the homogeneous solution parts go to zero, the particular solution parts go to being the forcing function that's out there. So these are always the two components that we're going to come up with for our forced harmonic oscillators here. There's always going to be the easy to access harmonic, or oh my gosh, I keep on saying harmonic. I'm thinking Calc 2 stuff. Homogeneous solution, as if we were equal to zero on the right-hand side, just make the problem easy. The particular solution, we're always going to sort of guess our way to what the particular solution component should be. And that should be the part that becomes the forcing function when we plug everything back into the differential equation there, all right? So the question is this always going to work? And the answer is no, but we can just guess harder, all right? So today, all we're really going to look at is just that being the left-hand side over there. So here's my deal. So basically the deal is that our oh my gosh, I can't stop saying harmonic. Our homogeneous solution should still be the same because the left-hand side didn't change. So for x sub p of t, let's make a guess. And what we learned from last time is that we should guess like a constant multiple of the thing that we've got, especially when we've got these exponentials that look like this. So like a k e to the negative 2t. So if that were the case here, I guess I actually need to give myself some actual room here. I'll bring it back in a second. So I'm going to go ahead and guess that x sub p should be equal to k e to the negative 2t. Then x prime of p should be negative 2k e to the negative 2t, and x double prime of p should be positive 4k e to the negative 2t. We're going to go ahead and throw all those guys into our equation here and see if we can find a value of k that's going to do this for us. Come on, Microsoft Word, don't start sketching out on me there. You can recognize what I'm drawing there. So what are we getting right here? I've got, I guess all the e to the negative 2t's are kind of going away here. I'm getting 4k minus 10k plus 6k equals 1 over here because I divided everything by e to the negative 2t. And what I'm seeing here is that we're getting 0 equals 1. So doesn't look like there is any value of k. That makes our guess of x sub p of t being equal to k e to the negative 2t work. Right? If it did, we would have just found a k value that would have actually made it happen right there. So that guess that we just made just straight up didn't work, right? We guessed k e to the negative 2t. We threw our guess into the differential equation. We were hoping to solve for a value of k that made it true, but we ended up leading ourselves to the equation 0 equals 1, meaning there must not be any value of k such that k e to the negative 2t is a viable candidate for our particular solution. So that's kind of a bummer. But fortunately, we've seen some stuff that's happened previously this semester where this happened, right? Where we wanted to build some exponential component to a solution, but the exponential that we guessed wasn't really going to work out. So what did we do to that? So what did we try earlier this semester when we wanted that exponential piece to work, but it didn't, right? And if you recall, in our repeated eigenvalue scenario, what we had to do was we had to take our k1 e to the lambda 1t plus k2 e to the lambda 2t, is we had to alter this because we had a repeated eigenvalue. And so instead we got like a k1 e to the lambda t plus k2 plus t k2 e to the lambda t. So remember, with our repeated eigenvalue situation, we ended up getting a component that didn't just have e to the power of, it had t e to the power of. So based on the fact that that worked out for us before, let's go ahead and see if we can make that guess work out here. So our new guess is x sub p of t being equal to k t e to the negative 2t. It needs to be a 2t, otherwise there's no way it's going to match up with our forcing term on the other side over there. So let's go ahead and see if we can get this guy to go ahead and work out for us here. So obviously it's going to be a little bit more annoying here when we go ahead and take our derivatives, because we now have a product rule that we've got to pay attention to here, but we can still make that guy happen here. So in this case here, x prime of t is going to be, so we take the derivative of t first, and we leave the exponential alone. Then we take the derivative of the exponential, and we leave the t alone. So we're going to get a minus 2k t e to the negative 2t. Right? The derivative of e to the negative 2t pops us out the additional negative 2. We kept the k and the t. Now to get our second derivative, this one's pretty easy. Negative 2k e to the negative 2t. I'm going to get a minus 2k times the derivative of 2e to the negative 2t. So the derivative of t gives me e to the negative 2t. The derivative of e to the negative 2t gives me negative 2t e to the negative 2t. And I can simplify this a little bit right there. Looks like that's really negative 4k e to the negative 2t minus 2t e to the negative 2t. So I've got my zeroth, first, and second derivatives available to me now. So now let's go ahead and see if we can make one of these guys work out. So we've now got I'll just switch to a new color here so we can kind of keep some visual distinction here. Our differential equation that we're trying to solve is this guy here. And I'm going to go ahead and plug in all my components and see if we can find what value of k makes this a good guess, if any. We saw above that sometimes the answer is not. That's not a good setup right there. So if I do this guy here, what am I going to get? I'm going to get a negative 4k e to the negative 2t minus 2t e to the negative 2t plus 5 times my first derivative is this guy right here, k e to the negative 2t minus 2k e to the negative 2t plus 6 times my original guess, kt e to the negative 2t. And we're thinking that's going to be equal to the e to the negative 2t on the far side over there. So let's go ahead and expand this and see what we end up getting. I'm getting a negative 4k e to the negative 2t minus 2t e to the negative 2t plus 5k e to the negative 2t. Okay, here's what I'm going to do. I'm going to back up right now, and I'm going to say, let's divide this whole dang equation by e to the negative 2t, since it's in literally every single term. So negative 4k minus 2t. By the way, should that not have a... That should have a k on it right there. I feel like I missed my... That's a plus 4k right there. Notice here I forgot to do my distribution. That's a plus 4k. I was like, where'd the k go on that thing right there? Okay, all right. So now I'm going to go back and fix this over here. That should have been a plus 4, plus 4. All right, now we're cruising. Plus 4k t e to the negative 2t. So I'm just going to write this as a plus 4k t. Here I'm getting a plus 5k and a minus 10k. I think I'm dropping some other terms here. Okay, that should be my first derivative, so there definitely should be a t sitting right there. So minus 10kt. And over here, we're going to get a plus 6kt equals just 1, right? So what I'm going to have to do, and notice here, that's because I divided the whole equation by e to the negative 2t, so that left me with a 1 on the left-hand side. So what I think that I'm getting here now is I'm going to group up by my power, how much t do we have. So I'm seeing negative 4k plus 5k. That's the stuff with no t's on it, plus 4k minus 10k plus 6k is how much t stuff we should have on the right. Now you should notice we shouldn't have any t components on the right, and that works out good because we did end up getting 0 right there, so that makes sense. The other thing that you can see over here is it looks like k is going to need to just be equal to 1 is all I'm ending up finding from that all that work that we did right there. So it seems like our particular solution, therefore, should be t e to the negative 2t. So it looks like by making a stepped up guess right there, we can find scenarios where we can still make a guess work out. So again, if your guess didn't work, if you got led to an impossible equation, just guess harder. Throw in some more terms in there. If this didn't work, I would probably try a t squared e to the negative 2t or something like that. See if we can make all of our terms work out in our differential equation that's over here. So, I should say, well, let's at least state our general solution there. Right, so we got our homogeneous solution that we carried over from the previous problem that we got from our eigenanalysis, plus the particular solution that we got from the method of undetermined coefficients, that we guessed a solution and we found the coefficient of a constant multiple of just 1 that made it work out associated with the differential equation that we had here. All right, so let's look at interpreting these, and this is going to help us figure out what's really the deal with this whole homogeneous versus particular thing. And my question to start with is this, or I guess I'd say we want to do a comparison of damped oscillators that are unforced versus those that are forced, right? That's kind of our distinction today. We've only looked at unforced in the past, right? So what happens to all damped, unforced harmonic oscillators? We already answered this question when we talked trace determinant plane. If you'll recall, we looked at some of the coefficients that have to crop up, like what types of coefficients are possible out here, and we saw that this p and this q are always going to have to be positive quantities, which means they're actually going to give us always, what, negative trace and positive determinant always. And so we saw that out there in the trace determinant plane, we were only looking at the second quadrant, and we saw things like sinks, degenerate sinks, and spiral sinks. So what this says to me is that we can really only get one of our sink type behaviors. And that should make sense to you because we are experiencing a damping force, meaning that is going to make our amount of motion get smaller over time. And there's no forcing term to reintroduce extra motion. So what should happen to every damped harmonic oscillator is it should eventually come to rest. That seems to make sense to me. Now, what you should notice is that the solution to a damped unforced harmonic oscillator is really our harmonic solution here. And so it seems like this should be going to 0 as time goes to infinity out there, right? And this just says the solution to any of these unforced harmonic oscillators is going to eventually say, oh, you're not moving out, right? This is the child on the swing. You push them once, they swing back and forth, they eventually come back to rest. You pull the mass on a spring and you let go, and it's going to wobble back and forth, and it's going to eventually come to rest. All of these things are going to do that, right? That's the nature of a harmonic oscillator. If you set it in motion and leave it, if it experiences any damping at all, that is eventually decaying the amount of motion that we're experiencing over time. And if you go long enough out in time, there will just eventually be no motion out there, right? So that's what happens in our unforced scenarios. So now, what you should be thinking is, well, how is this different if there's a forcing term involved, right? So given that x of t is a solution to a damped, unforced harmonic oscillator, we're going to get that our solution is just going to go to 0 as time goes to 0 because our sink type solutions are the only solutions that are available if there is a damping force. Therefore, in any damped forced harmonic oscillator, it should be the case that, I'm now thinking, just making like a limit statement here, limit as t goes to infinity of x of t. Well, in a damped forced oscillator, we're going to get our limit as t goes to infinity. X of t is really going to be our harmonic solution plus our particular solution, and that's going to go to just 0 plus whatever happens here, right? So basically what that's saying to me is that the particular solution is what's going to define what we're looking, or sorry, yeah, our particular component is going to always define what our solutions are going to look like in the long run. So we're going to expect that the long-term behavior of any forced harmonic oscillator will match the particular solution in the long run. So the two things that says to me. One, that says to me, at first, when you release it, there could certainly be some weird behavior going on associated with the homogeneous solution here. As time goes on, we're expecting our motion to only be that associated with the particular solution. And let's go back to the child on the swing example. Suppose my wife puts my child in motion on the swing. She pulls him all the way back, and she lets go, and he starts swinging. All right? Now, if I'm a terrible father, what I could do is I could just walk up and I could say, regardless of where he's at in his swing, I could just go up and shove him, and I can shove him every 2 seconds. Well, maybe it's that he's in his downswing back towards me, and I just shove him right in the back, snap his neck back right there. It's bad parenting right here, but good physics example. What's going to happen is that his motion is still going to be partly defined by the swinging back and forth from his mother releasing him. That's the homogeneous solution. That's what was happening when there was no forcing happening. But if I give him that shove in the back, regardless of where he's at in his swing trajectory, it's going to sort of like screw him up at first. But what's eventually going to happen over time is his swinging motion is eventually going to be perfectly matched by my pushing motion. It's going to be very jarring for the first push because it's going to jolt him into a new pattern of swinging. But eventually, his swing is going to exactly match the pushes that I'm then providing for him, right? So this is saying to me, you could be doing whatever you're doing at first. The homogeneous solution is sort of describing what would happen if we left the whole thing alone. The particular solution is saying, I'm going to come in here and I'm going to incorporate some of my own force, and what we should expect to happen is that that force is sort of the dominant descriptor of the behavior in the long run, but maybe not at first. Maybe there's sort of a period of time where things are sort of working to meet that motion right there. Another thing I want to point out is that I keep on describing to you periodic things, and we're not talking about sinusoidal forcing until the next section. But I do want to say to you, we're going to look at some graphs right now. The graphs aren't going to be very satisfying. Next section of 4.2, the graphs are going to be incredibly satisfying as we see things sort of converge on sinusoidal functions graphically. So I just want to say we are going to look at some graphs, but expect to see way more satisfying visualizations of what we're talking about in 4.2. The sinusoidal ones just end up kind of like, I don't know, they meet my intuition about this topic a little bit better. So, as our last example here, let's go ahead and look at this guy. So the two important things here, or I guess three important things here are this. One, we've got a constant instead of an exponential term on the right. So a little bit different there for our guess. Two, we've been given initial conditions. So rather than having a K1 and K2, we'll actually solve for a particular uh, for a specific version of the general solution. I want to be avoiding the word particular now since that's our x sub p. Three, we're going to look at a graph of this, and what we're going to expect to see graphically is we're going to expect to see the general equation that we get for our general solution here is going to do wonky things at first, but then we expect it to follow whatever the behavior is of just the particular solution in the long run. And we'll look at that guy graphically here. So let's go ahead and see if we can do this. And by the way, you should recognize that all that we're doing here is we're making smart guesses. If our guesses don't work, we're making more guesses. There's not some like overarching like extreme strategy that's going on here. So I think it would be a really good call for you to pause the video right now and see if you can just guess your way to getting this guy to happen right here. You know that your homogeneous component of your solution is exactly the same as what we've come up with before because we have not changed the left-hand side of our differential equation. The only thing that's changed is that we are now applying a constant force of 8. Constant. It's always being applied to the system. It's just that constant push of 8 right there. So let's do this. Our homogeneous solution. All right, so I just want to restate this here. We've looked at the left-hand side of every second-order differential equation we've seen today has been the exact same. And that's the only thing that determines our homogeneous solution. We always just say, pretend the right side was 0. If there were no forcing, what would happen in this system right here? That's what we're asking with our homogeneous component of our solution. So we're still getting the same x sub h right here based on the two lambdas that we get. If 8 were actually 0, then we could do our simple version of our eigenanalysis, just go straight to our characteristic polynomial, straight to getting our eigenvalues, straight to taking or writing out our solution in terms of x right there. What we're really here to talk about today is our particular solution. We need to make a good guess here. All right, so what we need to do is we want to make a guess for our particular solution, and we want this to work out to match up with our forcing function of 8, right? So you should notice in this case right here, it doesn't make sense for me to guess like exponential things because then I'm probably going to get out like an exponential function, right? So since I've been given constant things, it kind of makes sense that I should guess a constant, right? But I've learned a lesson. So The lesson that we just learned in the previous example was, I'll scroll back up, is that just guessing our most basic guess sometimes doesn't work. Sometimes we want to introduce something like a coefficient of t on front, right? So that would lead me to believe that we should maybe guess x sub p of t to be like t times b, right? Or b times t. I guess I should write that as the b looks like it's the coefficient, t is our variable, bt. And I'm going to say, let's do both. So here's the glorious thing about our method of undetermined coefficients. You don't necessarily know what components are going to actually belong in the particular solution until you've done the math. Sometimes it turns out that you include components in your guessed solution that aren't part of the particular solution. That's totally okay, because in the method of undetermined coefficients, you're just going to find the coefficient on that term to be 0, meaning no, that didn't belong in there. 0 of it is how much of it should be in the particular solution. So I'm going to go ahead and make my guess. I want to make a robust guess here, saying it might just be a constant, but it might be a constant times a linear. So let's do both. This will now encompass the possibility that my guess. So maybe now we're going to find that our particular solution should just be 5. Maybe we're going to find that our particular solution should be 5t. Maybe we're going to find that our particular solution is 3 plus 6t or something like that. All of those formats are going to be checked all at once by using this more robust guess right here. And notice, like, maybe I think there's some like trig terms. I could just do this, and guess what I would end up finding for C? I'm definitely going to find C to be 0 in this case, because I clearly don't have any trig components on the right-hand side of my equation right there. I could include it, and I would just end up algebraically solving, and I would find that C is equal to 0, meaning there are 0 components of the sine term in your guess out there. So I'm not going to go ahead and do that, because I would just get 0. But the point is, with your guesses out here, include any terms that you think might be in there. You don't have to do guess by guess by guess. Build the biggest, most robust guess that you can build that's not annoying to take derivatives of and actually plug into your differential equation, and guess the whole dang thing all at once. And if you get zeros for some of your coefficients, no problem. So based on this guess right here, I'm getting that x prime of t for my particular solution is just b, and that x double prime of t for a particular solution is just going to be 0 right here. So if I go ahead and I try and solve my differential equation based on this particular solution right here, then I'm going to go ahead and throw all this stuff in now. So I'm going to get my x double prime plus 5x prime plus 6x equals 8. X double prime is just 0. X prime is just b. And 6x is a plus bt. And that should all be equal to 8. So it looks like I'm getting 5b plus 6a plus 6bt is equal to 8. And so the thing that I'm seeing here now is that there is no t components on the right-hand side. So I'm going to think of this being written as 5b plus 6a plus 6b times t equals 8. Sort of like, and I'm going to just write it over here, plus 0t, right? So it seems to me like I can match these guys up now. It seems like we should be getting that 5b plus 6a is equal to 8. And it seems like 6b is equal to 0. The amount of t stuff on the left has to match the amount of t stuff on the right. The amount of constant on the left is going to match the amount of constants on the right over here. So it seems to me like I'm going to find that... oh, wait a minute. Don't I have a... Do I have these backwards right here? Sorry, I'm just, my notes have a ever so slightly different term in them here. Oh, I see why. Okay, that's okay. No, I'm all good right here. In my notes, I switched this so that this was a 6 and so that this was a 5. Ever so slightly different problem right here, so that's why I'm getting something ever so slightly different than my notes. So what this is saying to me is it looks like b is equal to 0. So then coming over here, I'm going to find that 6a equals 8, and that a should therefore be 8/6, or I should be finding that a is going to be 4/3. So it seems to me then like my particular solution, and again, this just said to me, oh, hey man, you guessed that there was going to be a t component in your particular solution. Well, b equals 0 says, nah, there wasn't actually any t component. You only had the constant right there. So if we would have just guessed x sub p equals a, we would have just found a being 4/3 and nothing else. We included some extra components, found that they didn't actually belong. Nothing wrong with that at all. It's better than doing multiple layers of guesses. Do one nice big robust guess at the beginning and you'll find all the components that you need, and you'll find maybe that some components weren't actually necessary. So this says to me that my x sub p of t equals a plus bt equals just 4/3. So our general solution is x of t equals, and what do we get here? We got k1 e to the negative 2t plus k2 e to the negative 3t plus just 4/3. Now remember, our last part of this is that we had initial conditions. And then we'll look at a graph and we'll call it a day here. X of 0 equals x prime of 0 equals 0. So when I do this one here, I guess I'm going to get x of 0 is going to be k1 plus k2 plus 4/3 equals 0. So I can write this as k1 plus k2 equals negative 4/3. That's one equation that I have. The other thing I know here is that x prime of t equals negative 2k1 e to the negative 2t minus 3k2 e to the negative 3t. And then there's nothing over here because I took the derivative of x and the derivative of constant is 0. So I'm going to go ahead and apply the initial condition of 0 here. That's going to tell me negative 2k1 minus 3k2 equals 0. So I think I can go ahead and solve this system of equations right here. And maybe I'll do like a 2k1 plus 2k2 equals negative 8/3. So I doubled this equation. And down here I'll do a negative 2k1 minus 3k2 equals 0. And I'm going to go ahead and do addition right here. So those two go to 0. This gives me negative k2. And this gives me negative 8/3. So it looks like k2 is 8/3. And if k2 is positive 8/3, then k1 needs to be negative 12 8/3. Right, which is just negative 4. So it looks like we have found x of t is going to be equal to negative 4. Oh, I'm just trying to write my k again. We just solved for k. It's the negative 4. Negative 4 e to the negative 2t plus 8/3 e to the negative 3t plus 4/3 is the particular solution that passes through 0, 0, or passes through 0 with a velocity of 0. And what we know to expect and let's go take a look. So as our last thing for the day, let's go take a peek at a video here, or at a graph here in Desmos. I'm just going to graph this guy right there in Desmos. So negative 4e to the negative 2t, negative 4e to the negative 2x. Our other component there was plus 8/3 e to the negative 3t. Plus 4/3. And so what we can see here with this graph is that it looks like it's doing some wonky things at the beginning. We are passing through the origin, which is important. Why is it giving me double? That's weird right there. Okay. And importantly, what we can see is that we expect this to just look like the graph of 4/3 in the long run. And as I said today, we're getting some unexciting looking graphs right here. Where technically, yes, in the long term, this curvy function does look like it is just becoming the function y equals 4/3 in the long run. So it does look like our particular solution is the dominant descriptor of our behavior in the long run, but not necessarily in the short term. Here's where our homogeneous part's still happening right here. But again, this isn't very exciting. What's going to be way more exciting is when we do the same type of thing for our sinusoidal forcing ones above. Our long-term behavior, this function right here, is going to be like a trig function, and we're going to see graphs that are doing crazy things and then just settling down to just matching a trig function in the long run. That will be very highly satisfying right there. So this graph right here, not too exciting. I will throw it into the notes because it's technically the thing that we're looking at here, but not too terribly exciting. The exciting graphs are going to come up next week right here. All right, so I'll leave this guy right here in the notes. And I think that's all my comment down at the bottom says is, note that in this section, we looked at exponential and constant forcing terms. In the next section, we're going to look at sinusoidal forcing terms. They're going to be a little bit more exciting. We're going to do a little bit more than just make a guess and see that it works. We're going to see some cooler math and some cooler graphs out there for our sinusoidal forcing terms. So I will see you guys in section 4.2 where we hit up our sinusoidal forcing terms. We're still going to get the same idea that our general solutions are going to be equal to a homogeneous component plus a particular component. Finding the homogeneous component is still going to be extremely easy. We're just going to get to do our rapid fire straight to our characteristic polynomial, get some eigenvalues, state the solution. The particular is going to be the thing, just like today, that's going to require a little bit more work. It's just going to be dependent on a little bit more than just a guess. We're going to have to actually do some math to find the good version of that component there. So I'll see you guys for 4.2 sinusoidal forcing for the better math and the better graphs here. Have a good one.